Hello students, this is Dr. Swati Vitkar going to take a topic on operating system, and the topic name is dining philosopher problem. This problem is basically a classic problem of process synchronization. So there are various problems for process synchronization. One of the problems is producer consumer. Another problem is dining philosopher. So here you can see that there are, suppose over a round table, five philosophers are sitting at a time and they want to eat a rice bowl which is kept inside. Okay, so there are five forks kept. So there are some conditions that one philosopher either can think or can eat. And if he wants to eat, then he needs two forks. But for five philosophers, there are only five forks. So all five cannot eat together because in all they need 10 forks. But here only five forks are there. So they are sitting around a circular table with one fork between each pair of philosopher. There is a philosopher may eat or he can pick up the two forks adjacent to him. One fork may be picked up by any one of its adjacent followers, but not both. So suppose his adjacent philosopher has already taken two forks, then the neighboring philosopher has to wait till he finishes eating and keeping his fork back. So here you can see an algorithm. Void philosopher int I while true, and suppose his thinking is over, because as I told you earlier, he can do two things. One is thinking and other one is eating. So after thinking, now he wish to eat, and for that he is there are some rule. He has to pick up the left fork first and then right fork. Okay, so suppose philosopher P0 comes. You can see in the diagram P0 philosopher is having two forks, uh, respectively F0 and F1. So when P0 comes, he has to pick up F0 fork first and then F1 fork. So take fork I. I is nothing but index of the philosopher. So philosopher index is P0 here. So automatically I value becomes 0. So when he calls the method take fork I, then he will take fork 0 because philosopher's index is 0. So I value is 0. So take fork 0. He will take the fork 0 in the hand. And now he will take fork 0 plus 1, that is I plus 1 mod n. What is the value of n here? Total number of forks, that is 5. Okay, so I plus 1 is nothing but 0 plus 1, that is 1 mod 5, and 1 mod 5 is nothing but 5 only. So 1 mod 5 is 1. So he will pick up 0th fork and 1 fork, and then he will enter into the critical section and he will start eating. After eating, he can put fork I, that is 0. 0th fork he will put first, that is left side fork he will put, and then he will put I plus 1, that is 0 plus 1 mod n. So 1 mod 5 is 1. So he will again keep back first fork or F1 fork, and then another philosophers can start eating. But if this condition is true when philosophers come serially, so if one after the other philosophers keep coming, then this particular method perfectly work fine. But now there are some cases where it may not work properly. For example, suppose P0 comes. he takes F0 fork first. And before he takes F1, P1 philosopher comes and he takes his left side fork, that is F1. So P0 is now waiting for F1, but P1 has already taken F1 and then now he is taking F2. So he started eating, he enters into the critical section. So P0 has to wait till P1 finishes eating and keeping back F1 and F2, and then only P0 can start eating. So this condition, this waiting condition is called as race condition. Race condition. So to avoid the race condition, uh, there are some solution for that. And one of the solutions is to use semaphore array. So it is an array of semaphores. So how many elements are there in the semaphores, or how many numbers of semaphores are there as the number of philosophers, or as per the number of forks, that is 5. Okay, so here we are using, so by using semaphore, race condition can be avoided. What do you mean by race condition? If one philosopher is eating, another one has to wait till he finishes eating and keeping back the forks. But semaphore is one of the solutions on this problem. And how it works? Suppose there are 5 philosophers, as you already know, P0, P1, P2, P3, P4, and there is an array of semaphores. So, as per the number of philosopher, suppose it is 5, then semaphores also would be 5. That is S0, S1, S2, S3 and S4. And all semaphore value is set to 1. So now here you can see, suppose P0 philosopher comes, then he would require S0 and S1. So there are two methods for the semaphore. One is called as wait and another is called as signal. So wait condition will put down or reset the value of semaphore from 1 to 0. 1 to 0. So suppose P0 philosopher comes, then it will enter into the wait method. That is wait, take fork S of I. What is the value of I here? As same as the philosopher index. That is, if P0 is the philosopher number 0, then I value is 0. So automatically semaphore value also would be 0. So P0 requires S0 and S0 plus 1, that is 1 mod 5, 1. So P0 philosopher requires semaphore number S0 and S1. So it will reset the value of S0 and S1 to 0 and enter into the critical section, and it will start eating, and then after the critical section is over or after eating, it will again set the value of S0 and S1 to 1, so that that semaphore will be released and it can be used by other philosophers. So now again it will work fine if they keep coming serially. But now we'll see another case here. So suppose S0, sorry, P0 philosopher comes, it will put down the value of semaphore number 0 and semaphore number 1 to 0. That is wait. Okay, and enter into the critical section. And suppose P1 philosopher comes, then P1 would require, you can see in the table, P1 would require semaphore number S1 and S2, and it will try to execute wait method. But wait method will try to keep the value of S1 to 0, but which is already 0 by P0. So, so P1 philosopher will be blocked, or that process will be blocked, and it cannot enter into the critical section at this moment till P0 finishes eating. Okay, now suppose at this moment P2 philosopher comes. P2 philosopher comes and it require S2 and S3. How do you define the number of semaphore? As per the index number of P, you can decide the index number of semaphore as well. So P2 comes, then S2 and S3 it would require. So S2 value is 1 only and S3 is also 1. So it will execute the wait method and it will after executing it will put down the value of S2 and S3 respectively to 0 and it will enter into the critical section. This means that P0 and P2 philosopher at a time, both of them at a time can eat. So this is the solution of using semaphore. So two philosophers can eat at a time. So you can say that mutex, we can use mutex also, but in mutually exclusion environment, only one method can enter into the critical section. But here by using semaphore, two methods also can enter into the critical section and both of them can eat together if both the methods are independent of each other. So you can see here across the table P1 and P0 and P2, they are independent and they would require different forks. So both of them can eat together. P1 and P4 also can eat together. P0 and P3 can also eat together because they are independent of each other and they can use the resources if they are available. So this is all about we need a semaphore. Just a minute.